This made your life easy. Now, what about the modulus? It's actually the axis of the cochlea. Why is it important? Because it has the cochlear nerve. Because at the end of the day, if you guys look at the cochlea, look at this picture. If you guys look at the cochlea, if we try to take a cross section in the cochlea, you're gonna see that what I already explained to you, that we have the vestibuli above, all right? Why it stopped working? Yeah, so you have the vestibuli above. So this is the scala vestibuli. This is the scala tympani, and you have the basilar membrane that as you bring the sound waves all the way from here and it turns around the helicotrema and it reaches here, this is going to vibrate. And as they vibrate, you're going to approximate the basilar membrane on which the hair cells are sitting on the top into the tectorial membrane, and once they approximate, you are going to activate the hair cells to detect these sound waves and transduce this energy into something that your brain understands and interprets it as sound. Now, how is that happening? Okay, we will talk about again this thing, but I just want you to see that if you look at a cross section in cochlea, you need to know that you have the scala vestibuli above, you have the scala media in the center, and this is actually within your membranous cochlea, because I already explained to you the idea how the membranous cochlea is actually embedded in the bony one, all right? This is filled with endolymph, all right? And this is filled with the perilymph, all right? If I have it continuous with the vestibule, we're gonna call it scala vestibuli. If we have it continuous with the secondary tympanic membrane, we call it scala tympani. This is above, this is below, and the communication is the helicotrema. And as I proceed with these sound waves, I'm gonna vibrate the basilar membrane, and which have the tectorial on the top, and as I approximate them together, I'm gonna have the activation of the hair cells. So if you guys look at a histological section that shows you what happens inside the cochlea as you receive the sound waves all the way, it turns around, and it turns around from the scala vestibuli through the helicotrema, it goes to the scala tympani, and it proceeds. This is what's going to happen here. You're going to vibrate the basilar membrane, and on top of that, you have your hair cells. You have the tectorial membrane on the top. All right. If we try to zoom in, hold on. If we try to zoom in, okay, you guys can see that on the top of the basilar membrane, you have the tectorial membrane. Okay, so these are the hair cells, and as you approximate them, you are going to activate these hair cells, and the hair cells are what we call a transducer. These are transducers. They are mechanoreceptors. What does that mean? It means they have the ability to transduce, to convert, to change the mechanical energy, which is basically vibration, all right, the sound waves themselves, into an electrical energy or chemical energy that your brain is going to understand by the opening of the ion channels and activating the bipolar neurons. And these bipolar neurons, their bodies are sitting in the spiral ganglia, all right? So as you get out of this, you have your spiral ganglia outside, you have all the bipolar neuron cells, and you guys know that the bipolar neurons are neurons that they have the dendrites, the receiving part of them, and they have their axon, the sending part, from two poles, one pole and another pole, and these are the neuronal cells that we get to see them in the sense organs, all right? So I have the cell bodies of these bipolar neurons, all right? I'm sorry about the bad drawing. These cell bodies are going to form ganglion, all right? So collection of cell bodies outside the central nervous system is what we call the ganglion. So here we have the bipolar neurons in the modulus, in the axis, in the bony axis of the cochlea. I have them here. These are spiral ganglion, all right? they are sending their dendrites to the hair cells. The hair cells are detecting that sound wave. They are, as I showed you guys previously, these are the hair cells. They are going to transduce, and they are going to get to activate, open the channels, transduce. They are going to convert that energy into something that the neurons understand, and then they're gonna get this information all the way to the through the dendrites of the bipolar neurons. And then here we have the cell bodies of the bipolar, and from there you are receiving all the axons of the bipolar neurons of the spiral ganglion all the way in the modulus of your cochlea, all the way through the cochlear nerve, and from there you have it through the internal acoustic meatus, and it takes you to a cochlear nuclei present in the brainstem. We're not going to talk about them now, but we're going to talk about them when we explain the neuroanatomy series, right? So this is how we transmit this sound from the end of the journey. I'm gonna explain to you again one more time on how we transmit the sound waves as we proceed. But now, what would be the blood supply? The blood supply of your inner ear is actually coming from the ICA. It's from the anterior inferior cerebellar artery. We're gonna explain that artery into more details as we proceed. It's actually a branch of the basilar artery. All right, so we have on the pons, you have the basilar arteries. All right, so whether it's coming from the basilar itself or from the ICA, which is actually a branch of basilar, at the end of the day, the cochlear branch that goes to the cochlea and the vestibular branch that goes to the or the vestibular system, they are basically branches of the anterior inferior cerebellar artery or the basilar artery. All right. Now the question is, how do we hear? I already explained to you the story from the end. I'm going to explain it to you one more time. So as you have your auricle collecting the sound waves from all around you, you're going to have these sound waves transmitted. They're going to uh, uh, um, um, vibrate the eardrum or the tympanic membrane. The tympanic membrane is going to push against the MIS, the Milius, Incus, and Stapes. And these bones, thanks to them, they are going to convert the high amplitude, or low frequency waves into short amplitude, high frequency waves. Why is that? Because in the middle ear, you guys, this is air. Okay, so in the air, it's fine for the sound waves to have a high amplitude, low frequency. But when I get this information into the fluid around my cochlea, it really needs to be short amplitude, very high frequency wave in order to be able to be transmitted into the cochlea. All right, so that's going to be done by the three ossicles that they are going to vibrate and push against the oval window. And once they enter here, this is the type of the frequencies and the type of the I forgot the word. Um, I think the waves. What do we call them? Waves. All right. So this is how they are going to get into the scala vestibuli. As I told you, we call it scala vestibuli because this is continuous with the vestibule. All right, because the vestibule is the entrance, remember? All right, so once you get them here, you get it all the way through the scala vestibuli above your scala media, and the scala media is actually what's inside the membranous cochlea. And thanks to the helicotrema, that will help me to redirect these information into the scala tympani, and I take it all the way to the round window, and the round window is actually covered by the secondary tympanic membrane. Why it's important to me to have it to the tympanic? Because on the top of that, and what separates the tympani from the media, and the media is a more important thing, yeah, because the hair cells are inside the media, this is going to vibrate the basilar membrane, okay? And as I vibrate that, I'm going to approximate this to the tectorial, and I'm going to activate the hair cells. And like I said previously, I'm going to transduce this kind of mechanical energy. That's why we call them mechanoreceptors, into chemical and electrical energy by the opening of the channels. And more details on that you're going to have it in the physiology lessons, all right? And as you activate the hair cells, you are going to send the information to the bipolar neurons and then to the cochlear nerve, and from there you get them to your brainstem, all right? Okay, so here again, what I explained to you previously, here is the basilar membrane. This is the organ of Corti that has the hair cells that most of your cochlear nerve is formed by inner hair cells, but you still have something called outer hair cells, and these hair cells are going to detect different kinds of frequencies. They're going to help also in processing of the sound waves and the information of hearing into the bipolar neurons, and from there you get them to the spiral ganglion. And we have something called stria vascularis, and this is important because they are going to secrete your endolymph that is in front of in front inside your the cochlea, all right, the membranous cochlea, scala media, all right. Okay, so this is the vestibular nerve. We talked about it. Now, how do we balance ourselves? Now, moving on to the last part of the inner ear, it's basically the vestibular system. Now, how does the vestibular system work? I made to you guys a small, nice summary to help you to memorize the difference between the utricle and saccule. The utricle and saccule are actually these dilatations, and they are going to be important to detect the linear acceleration. All right, if I am moving forward, backward, all right, without any angular kind of movement, thanks to the utricle and saccule, they are going to help me to balance myself as I move. Now, if I have utricle and saccule, the utricle is important for the linear acceleration in the horizontal plane, okay, the utricle. But the saccule is important for linear acceleration in the vertical plane. What does that mean? It means this is going to balance my head if I had sideways head tilts, sideways. But if it's upward, downward, forward bending of my head and backward, this is going to be done by the saccule. What is the sensory organ exactly inside the utricle and saccule? We call it macula. What is macula? I'm going to explain to you that in a bit, all right? So what happens actually? What is macula? What is macula of utricle and saccule, and what is crista ambularis? This is actually, you guys, the epithelial cells inside which you are going to find the hair cells, the mechanoreceptors, the cells that are going to change one type of energy to another. So the word macula means the epithelial cells inside which you have your hair cells, the mechanoreceptors, that are going to detect one type of energy, transduce it into another type of energy, and fire these neurons and take the information through the vestibular nerve to your nuclei in the brainstem and help you to balance yourself. Now, how does that happen? If I tilt my head, it depends on the type of the head tilt, I'm going to activate whether that is in the utricle or saccule. It depends on the type of my head tilt, like I said previously. As I move, I have these, the ear stones, they are sitting on the top of a gelatinous material. As I move my head, these stones are going to move, all right? If they move, they are going to bend the cilia on the top of the hair cells. I have a hair cell, and on top of that, I have stereocilia, a lot of stereocilia, maybe 3 or 4, something like that, and one long kinocilium. If these stereocilia move towards the long kinocilium, it means this is activation of the hair cell. It means the channels are going to open. Okay, it means I'm going to transduce this mechanical energy, which is the movement of my body, into this electrical energy. Once I does that, once I do that, I'm going to activate the hair cells. I'm going to activate these nerve um, dendrites. I'm going to take this information all the way to the vestibular division of the vestibulocochlear nerve. All right, so this is what we mean by cochlea, and this is how we do the balance in a simple way. Now, what happens with the semicircular canals? You guys know that we have the vestibule that has the macula and saccule, and then we have semicircular canals, all right? And this is for the angular acceleration. And also we have the cochlea, صح? So the cochlea is just for hearing, and this is done. Now we talked about the vestibule. We have the utricle and saccule, and this is for the linear acceleration only. It depends on the type of head tilt. I'm going to activate them, and we talked about them. Now, what happens in the semicircular canals? These are important for the balance when we have an angular acceleration. Any kind of rotational movement, it's going to be detected by the semicircular canals, and in that case, I'm going to balance myself. So angular acceleration by semicircular canals. Which part exactly? It's the crista ambularis. What do we mean by crista ambularis? Again, it's the same idea. Crista ambularis means the epithelial cells. I have epithelial cells, and these cells, they are having the hair cells that will help me to detect this information and transduce it into something that I can understand. All right. What does the word ampulla mean? What does the word ampulla mean? Guys, the word ampulla means dilatation. If you guys look at your bony semicircular canals, you will find that the bony one has a dilatation at the end of it. This is what we mean by the word ampulla. All right. So what does crista ambularis mean? The crista ambularis, it's a crest. Can you guys see this crest? Okay, that's made by the epithelial cells inside which you have your hair cells. This is the crista ambularis. It's a crest of cells inside the ampulla. But what about the copula then? The copula is the gelatinous material, the gelatinous substance that is going to fill in the space between your ampular wall and the crista ambularis. But what does copula mean in Latin? Copula means communication. It's the connection between stuff. So because my ampular wall is far away from the crista ambularis, the copula is actually the gelatinous substance that is going to fill in the space between the ampular wall and the crista ambularis. Why do I need that? I need it because as I do a rotational movement, I'm going to move my body in a rotation. And as I move my body in a direction, the gelatinous material that is filling my semicircular canal by inertia, it's going to stay in position. It's going to stay back. As it stays back, we will feel that it moved in the opposite direction. Actually, it's not going to move. It's only that the semicircular canal itself, it's moving with your body in one direction, and because of the inertia, this is staying back, so it's going to move in the opposite direction. All right? When we compare it to the movement of the semicircular canal, when that happens with rotation, this is going to bend the cilia. Again, the same concept we explained previously. They're going to move the stereocilia toward the kinocilium. If I move them toward that, this is going to cause depolarization. The ion channels are going to open. We are going to activate these hair cells. We are going to transduce the mechanical energy into electrical energy. And then I'm going to activate these neurons. I'm going to bring the information by the vestibular nerve all the way from the semicircular canal, and I take it all the way, and it exits through the internal acoustic meatus in the posterior cranial fossa, and I take the information to the vestibular nuclei, And how do we do that? Because we are detecting these changes by our proprioception. More details about how we process this information is going to be covered in the neuroanatomy module playlist series. I hope you guys understood everything. I hope I made your life easy by these small notes into the ear. And thank you guys for watching, and see you inshallah.